My problem is the Watson and Crick DNA. The phosphate backbone is composed of a ribose sugar and a phosphate group. In the ribose sugar, the 1' carbon is the attachment site for a nitrogenous base. 2' carbon determines whether the ribose is deoxy or not. If it doesn't have a hydroxy group on the 2' carbon, then it is a deoxyribose. 3' carbon is the attachment site for the next 5' phosphate group, and the 5' carbon is the attachment site for the phosphate group. The phosphate backbone of DNA is like the railing of the staircase. Each strand has a 5' end and a 3' end. 5' end has a free 5' phosphate, while the 3' end has a free hydroxy on the 3' carbon. The two DNA strands run anti-parallel. One goes from 5 to 3, and the other goes 3 to 5. The two types of nitrogenous base are attached to the 1' carbon on sugar are purine and pyrimidine. Purine is a double ring structure while pyrimidine is a single ring. In purine, there is adenine and guanine. The mnemonic I use is pure as gold, where P is purine, A is adenine, and G is guanine. The two types for pyrimidine are thymine and cytosine. Hydrogen bonds allow base pairing between purine and pyrimidine. A pairs with T and C pairs with G. The base pairing can be thought of as the steps to the staircase. It holds the two railing or backbones together. The shape of DNA is spiral. There are two forces that stabilizes this structure, hydrophobic interaction and hydrogen bonding. The hydrophobic interaction is the most stabilizing. Hydrophobic interaction is maximized by base stacking, which is an arrangement when the bases are stacked inside the double helix structure. Since nitrogenous bases are hydrophobic, they don't like to come into contact with the aqueous environment in our cells. When fat comes into contact with water, they form spheres, which minimizes the surface area exposed to water. In a spiral shape, the bases are all gathered in the center to minimize exposed surfaces to water, and the phosphate backbone is exposed to aqueous environment. Since the backbone is negatively charged, it makes them hydrophilic. The hydrogen bond between the base help hold the backbone together like floorboard of the staircase. The spiral structure is composed of major and minor grooves. Major grooves are where the backbones are far apart. Minor grooves occur where the backbones are closer together. Lastly, when we spiral the staircase, it can be left-handed or right-handed, depending on the way it is twisted. Imagine you are walking up the spiral. Whatever hand you use to hold the railing or phosphate backbone is what hand it is. So if I am using my right hand to hold the railing or backbone while walking up the spiral, then it is a right-handed DNA. The Z form of DNA is left-handed, and the B form of DNA is right-handed and most stable. Almost all DNA are found right-handed. The two negatively charged phosphate backbone repel each other. This repulsion is a major destabilizing force. When salt is added, it neutralizes the negative charges on the backbone, thus lowering the repulsion force. The smaller repulsion force stabilizes the DNA and increases the melting point. Reducing the negative charge also decreases how hydrophilic the backbone is and lower the solubility of DNA in aqueous environments.